Okay, let's get started. So, okay, today we are going to discuss heuristics and approximation algorithms. Let me start with just the general idea of heuristics, right? And the motivation is perhaps clear after we did NP completeness, and so many simple and interesting problems that we want to solve are NP hard, or sometimes even worse. Sometimes they're undecidable, or somewhere in between. There are complexity classes which are beyond NP, like X and P space, and higher levels of difficulty. And there are things we want to solve which fall in these categories, which means basically that we don't have an efficient algorithm, which is efficiency here means polynomial time algorithm, to solve them, right? So what do, right? It's not the case that these problems are not there. We still have to deal with them in some way. What do people do, right? In practice, when you have to solve something that doesn't have an efficient algorithm, they do various things, right? I just want to go over a few ideas and then discuss approximation algorithms, which is one particular type of algorithms, okay? So one thing people do is like, okay, I can't solve this general problem, but maybe I'll figure out a special case that I can solve, right? And I say, okay, I'm only interested in this special case, or I somehow am able to tweak my general instance into a special case instance and then solve it and do something, okay? So that's one general idea of how to deal with difficult problems. But in practice, what most of the time people do is that, they either use some inefficient algorithm or some heuristic. What is a heuristic? Is something which is an algorithm which doesn't have very good guarantees on its performance, but it does something and it works on some subset of the instances, okay? So remember, what is an algorithm, right? And when we have they say we have an algorithm to solve a problem, we want it to work properly on all instances, right? It has to give the right answer and run in the right amount of time for all instances. So you relax that and say, oh look, maybe my algorithm will solve some easy instances, but maybe we'll give up on hard instances, right? So that's what people do in practice, right? When you're stuck with a difficult problem, you just do the best you can, right? Many times the instances that you get in practice are not as hard as the worst case instances. So this approach works well. And this is one thing that we'll emphasize in the rest of the class is we'll settle for suboptimal solutions, okay? That is, we want to find an optimum solution, right? That would be nice, but we can't get an optimum solution. We'll say, okay, we will try to settle for something which is not optimal, but what does it mean to be not optimal? Well, we will try to figure out what it means to be not optimal in a systematic way, okay? Okay, but first let's go back to NP and exp, right? Just to remember a basic fact. What is the set of problems in NP? These are all problems which have the property that they have an efficient certifier and a short certificate, right? That, somehow if I give you a solution, you're able to quickly verify that it is a valid solution, right? That's a class of problems, and many problems have that property, like Sudoku puzzles or homework problems or SAT or things like that. Okay, but we already saw that NP is a subclass of exponential time, right? Every problem in NP has an exponential time algorithm, right? Why is that? Because, you can run the certifier on all proofs of a length polynomial in the input size. If I give you, so what is a simple example, right? Take SAT. You run what is the certifier? The certifier is going to check, given a truth assignment, does it satisfy the formula, right? So you run the algorithm certifier on all possible truth assignments, and if any of them say yes, you say, aha, it is satisfiable. If any of them say, if all of them say or no, then we know the formula is not satisfied, right? It's very easy for SAT, but in general, all NP problems have an exponential time algorithm, right? Because you try all possible certificates of polynomial length in the input and run the verifier on all of those proofs, and if any of them you satisfy the instance, you know it is satisfiable, otherwise you say no. Okay? Okay, so for every NP problem, you have a brute force exponential time algorithm, right? So why not run it? Well, the running time is exponential, so it is not going to run very fast, so it will be slow. That's the main problem, right? Okay, so what is one way of making this exponential time algorithm run faster in practice, right? In the worst case, it will be is what's called backtrack search, right? So what is backtrack search? You are doing an exponential size search, but being a little bit clever about pruning, basically. Okay? So it works very well in practice for moderate problem size, right? You know, here is a figure for how it works, right? You know, as by an example. Suppose, you know, you have this SAT formula and you want to check whether it is satisfiable or not. Okay? What does trying all possible assignments mean, right? You can do something which is very dumb, like saying, you know, here is one assignment, I'll check if it is satisfiable, right? And then here is another assignment, I'll check if the formula is satisfiable. That's a very linear sized, you know, you guess assignments one by one, but we can generate these assignments a little bit more cleverly by going one variable at a time, right? It's a recursive algorithm. You say, okay, look, I have a formula, I'll check by setting this variable to 0 and to 1 and checking what happens if I do that, right? So instead of generating a full assignment, you generate the assignment one variable at a time and simplify the formula as you go along, right? This is called backtrack search. So here is, you pick a variable here, w. You say, okay, you know, is the formula satisfiable if I set w equal to 0? Is the formula satisfiable if w equal to 1? Okay? If the formula, and so you do this branching with one variable w and say, I'll set it to 0 and I'll set it to 1, right? Okay, what is the advantage of doing this incrementally? If you set w equal to 0, what happens? The formula simplifies, right? Okay, if w is 0, it means that, you know, there is this clause cannot be satisfied by w, so we delete that variable from that clause, right? Where is w? Here. So this clause cannot be satisfied by w because we are setting it to 0. So that means that this clause, this formula is satisfiable with w equal to 0 if and only if the simpler formula is satisfied, right? Yeah? Okay. So now we recursively try to check whether this formula is satisfiable. If it is satisfiable, then we know that the entire formula is satisfiable, right? If it is not, we don't know. That means that we have to go to this branch and check, maybe the formula is satisfiable with w equal to 1, right? Okay? Okay, if w equal to 1, how does this formula simplify? It means that if w equal to 1, this clause is already satisfied, so we can get rid of this clause and this clause, and right? Okay, and we get a simpler formula. In either case, we get a smaller formula, right? And we recurse, right? It's just like it's a recursive algorithm for satisfiability, right? Okay, well, in practice, what happens is the formula can simplify substantially, right? Depending on what the formula looks like, right? So instead of doing a brute force search, you can do a clever backtrack search, and at some point, see, look at this formula, right? What is the nice thing about this formula? This formula is what? A 2-SAT formula, right? All clauses have at most two variables, okay? We know an efficient algorithm for 2-SAT. So you don't have to recurse anymore. You can just use that algorithm to solve that formula, right? If at any point you get a simpler formula which you know how to solve because it has either 2-SAT or something, you just use an existing algorithm, right? So this is just a refinement or a practical improvement over brute force enumeration by doing incremental backtrack search, right? So you can do this and it works very well in practice for moderate size instances, and it also depends on the class of instances you get, right? So the people use this. This is called backtrack search, right? All right. Now the question is, you know, heuristics what does it mean to be heuristic, right? You know, so which variable should you pick first? That has a role in how to speeding this up, right? What are some ideas on which formula you should pick first? Which variable you need to pick first, right? What is a simple heuristic? if I gave you this formula, why did I pick W, or maybe I could have picked X, or all, right? Anything I could have picked, right? What is one simple idea that you may think of? Yeah.
Pick the one that appears the most times.
Yeah, I mean, if there is a variable that appears in many clauses, that reduces the size of the formula the most, right? So it makes sense to pick the one which occurs a lot of times, right? Okay, so I mean things like that you can do, and the another thing that may not be obvious is that if there are a lot of size 2 clauses, then and a variable occurs in many size 2 clauses, that's very good, right? Because once you pick a variable in a size 2 clause, in the resulting formula, the clause becomes size 1, right? Size 1 clauses are good. Why? Because if you want to satisfy it, there is no choice, right? You know what to do if you have a size 1 clause, right? So if there is a variable which occurs in many size 2 clauses, that's a good variable to check, right? So you can do all kinds of things, but it's a big industry, SAT solvers, right? Okay, and you know what are some examples? There are some examples of which formulas are satisfiable and easy for SAT, and that's a long history. I won't go into that, right? Okay, so that is what you call a backtrack search for sort of something like satisfiability when the answer is yes or no, right? But you can do something very similar for optimization problem, okay? And I just want to introduce one more idea of the notion of bounding, okay? And that's a very important practical heuristic. So I want to solve an optimization problem, okay, as opposed to a decision problem like SAT. So let me take an example, vertex cover, which we'll come back to later, right? So what is vertex cover? I have a graph G, and a subset of the vertices is a vertex cover if they cover all the edges, right? Right? Every edge must have one endpoint in that set. Then that's called a vertex cover, yeah? Remember the problem? And we prove that it's NP complete by a reduction from independent set, right? A complement, and we'll come back to that again. So it's an optimization. So what do we want to do when we want to solve vertex cover? Typically we want to find the smallest vertex cover, right? Yeah? Okay, I mean this is now an optimization problem, right? Because finding a feasible solution is trivial here, right? Because I can take all the vertices and it's a feasible solution. Right? The difficulty of this problem is not finding a feasible solution, which is the case with SAT. In SAT, you don't even know how to find a feasible solution. Here, it's finding the smallest solution that is the hard part. Okay, okay. So I mean, in this kind of optimization problem, what happens when you try to do branch? What does it mean to do branching, right? Or recursive search, right? How does the recursive search look like, right? So how will you come up with a recursive algorithm for vertex cover, where you want to minimize the size of the vertex cover? Incremental fashion, right? What should you choose first? You pick what?
The vertex with the highest degree.
Yeah, so I mean, let's even think about it. You pick a vertex and do what? You have two ways of, either you choose it in your vertex cover or not choose it in your vertex. If you choose it in your vertex cover, how does the graph simplify? What does it mean, right? I want to choose this vertex. So I'm finding the smallest vertex cover recursively by assuming that I want to pick this vertex, right? So if I pick a vertex, what happens? What simplifies? All the edges incident to that vertex are covered now, right? And then I recurse on the graph G minus the vertex. Yeah? Okay, what about the case when I don't pick the vertex? What should I do? Yeah? Yeah? If you don't want to pick this vertex, what should happen? Sorry? Now I have to pick all the neighbors, no? Why? Because all the edges incident to me have to be covered by who, right? I am not being picked, so all my neighbors have to be picked in the vertex cover, right? So I get rid of myself and my neighbors and all the edges incident to it, right? Okay, but what? So how does that look like? I mean, in the sense of in terms of a, so I start with G and I said, I picked a vertex, U is equal to 1. What does it mean that I'm picking, right? Right? I want to pick U, then I recurse on which graph? I recurse on G minus U, right? Okay. But what is my value? It is 1 plus the value of G minus U, right? Okay, but if I don't pick U equal to 0, what do I recurse on? G minus neighborhood of U minus U, right? Okay, but what is the value I get here? It is the size of NU plus whatever this guy comes out with, right? And so, okay. So I keep going that way, right? Picking a high degree vertex is good because either I remove a lot of edges, right? Because G minus U loses a lot of edges, or in the other case, I remove a lot of my neighbors and their edges too, right? Okay. Okay, but so I keep going along like this, right? So at some point, what happens is that, maybe you went in this direction, you found the value here, right? Okay. Now, how can I prune the search? I can prune the search if I somehow am able to know that if I go this way, I'm going to get too big a solution compared to what I already found, right? So as you are exploring, at some point you can avoid doing a search. So I need to explore this instance, but I already have an upper bound maybe on the size of the solution, right? I already found some vertex cover solutions, right? Some partial vertex cover solutions. So if I can figure out that, if I go down this path, I will not get any better solution than what I already have, then I can avoid exploring that path, right? So what do I need here? I need a routine which can quickly give me an estimate of the solution value in that instance. I don't always need an exact solution value. If you can find an estimate quickly, and that estimate can allow me to prune the graph, the search, then that will be helpful to me, right? So how can I get a quick estimate? Okay, that's a good question, right? Yeah? For a graph. Yeah, right? I give you a graph and say I want a quick estimate on an upper bound for the graph, right? Or a lower bound for the graph, right?
So any graph that's computed without greater than the upper bound, you're not going to search that?
Yeah, if I already have a solution, I need a lower bound, right? So suppose then see when I'm doing this exploration, I found that I know the graph has a vertex cover of size 100, right? If I know that if I go down and explore this graph, I will only get a vertex cover of size 101, then I don't need to go down that path, right? Right, so that means, I need to have a lower bound on the vertex cover size of that graph. Okay, combined with some other information, I can, so for example, in this case, if I know that, what is the value of my vertex cover in this, it is the neighborhood of U plus whatever is the vertex cover of this, right? Suppose I found, when I explored this path, I already know I have a vertex cover that I found. It may not be optimal, right? But I know that, I have a vertex cover of size 100, right, in the graph. Now I want to decide, should I explore this graph? But if I can estimate that, look, the neighborhood of the size U plus some lower bound on this graph is more than 100, I don't have to explore that side. Okay, but okay, how do I figure out a lower bound on this vertex cover? Okay, all I need is an estimator, right? I don't need an exact thing, right? Sometimes estimations are easy. Okay, okay. One idea which we'll come back to is to solve what is called a linear programming relaxation for that instance. Okay, and it will give us an estimate. Okay, lower bound, because it is a relaxation, it will give us a lower bound. Okay, and you can solve that efficiently. Okay. And if you can solve that efficiently, you say, okay, look, even I know that this side will not give me a vertex cover of size less than 100. So, okay, no way am I going to explore this because I already have a vertex cover of size 100. So you can do pruning like that, okay? So that's called branch and bound, okay? So we're branching, right, to figure out the optimum solution. What is bounding? Bounding is a strategy of saying that, I know how to get a lower bound in the case of minimization, a lower bound quickly. And if I have a bound, then I can avoid searching certain parts of this tree, right? That's called branch and bound. Okay. And it's a very common technique in operations research and in optimization and so on. Okay? So it's a practical method. Okay? Okay. So, let me briefly mention another important technique which is always useful even if you found some solution. It's called local search. Okay? It's also a very broadly applicable heuristic technique. What is local search? Local search is, I have a solution, can I improve it a little bit? Okay? And what is this called local, right? That means, see, how do I know whether I can improve a solution? Okay, that's hard to do because, it's hard, if the problem is hard, it means that if I have a solution, I cannot tell whether it's an optimum solution or not, right? Unless I actually figure out an optimum solution. So, but maybe I can improve it locally as follows, right? Take vertex cover. I give you a solution and I say, is this optimal solution? Okay, now you think, how do I check that, right? How can I reduce the size of the vertex cover? If I remove two vertices and add one more vertex and it remains a vertex cover, then clearly my solution is not optimal, right? I've reduced by one. Okay, but can I check that as a little bit easily? Maybe, right? How can I check whether I can remove two vertices and add one vertex and still remain feasible? I can try all possibilities, no? I take out two vertices from my current solution and try adding one. First, okay. First thing you have to do is the most basic thing, right? If I have a solution, I should make sure that it's minimal, right? What does it mean, minimal? That if I take out one, if it is still feasible, then it is not, it's not a minimal solution. What does minimal mean? That I cannot remove even one vertex from a solution and remain a vertex cover, right? Maybe your heuristic did something funny and it gave you a non-minimal solution. You should at least check that it's a minimal solution, right? Okay, that's the first step, right? Okay, the second step is, okay, maybe I can take two vertices and drop, I can drop two vertices and add one vertex and still remain feasible. Okay, that's called local move because I'm just doing simple moves, right, which I can do in polynomial time. So that's a very important important technique, and let me illustrate it with, and one of the ingredients, right, you basically start with a feasible solution and see if you can locally improve, and if you cannot locally improve, what you get is called a local optimum. Okay, and if you think about continuous optimization, all continuous optimization really is local search. Okay, many of you have probably heard of the word gradient descent or gradient descent, right? What is it really doing, right? You are at a point in space. Okay, is it optimum? Well, I'll compute the gradient. Okay, and then say if I can move along the direction of the gradient and improve my solution, I will, right? What is that? That's just simply a local search, right? You're just locally computing the gradient and moving. The global optimum may be somewhere else. We don't know where it is, right? When do you stop? You cannot improve locally by the gradient step, right? That's called a local optimum, right? The local optimum is not always a global optimum, right? Okay? But in a convex optimization, local optimum is a global optimum. Okay? So gradient descent will give you an optimal solution if you have convex optimization. But if you have a non-convex optimization, you will get a local optimum. But that's just basically trying to move locally, right? But in discrete optimization, we get what is called, here is a simple example of what is called a traveling salesman problem, right? In traveling salesman problem, what do you want to do? You want to find, say, in a metric space, or you have many points and you want to find a Hamiltonian cycle which is the minimum length. Okay? You want to visit everybody and minimize the length of the tour. Okay? It's actually, even deciding whether a graph has a Hamiltonian cycle is NP hard, but assume that the points are in the plane for simplicity. Okay? Then it's easy, right? There's always a Hamiltonian cycle because there's a complete graph. The only question is the cost of the Hamiltonian cycle, right? Because it's a simple graph. A complete graph always has a Hamiltonian cycle. So okay, so here is a current cycle. Does this look optimum to you? These are points in the plane. Does this traveling salesman tour look optimum to you? Why not, right? Can you improve it? Okay, Well, you can improve it like this, right? Why is this, okay, you say, is this an improvement? Oh, it depends on the length of this compared to this length of this, right? Okay. Here is a simple geometric fact. If in 2 dimensions, if you have 2 edges which cross, flipping those edges will always reduce the cost. Okay, it's a simple basic elementary geometry. Okay, here are 4 points, right? And these 2 edges cross, right? I replace this with these 2 edges which don't cross. One can prove that whenever that happens in 2D, the length of these blue edges will always be less than the length of those crossing edges. Okay, so if I give you a tour on the plane, you should, if any 2 edges cross, it is not optimal tour. Okay, you can flip it, right? Okay, so this is called a 2 exchange heuristic, because you find 2 edges and see if you can flip those edges and reduce the cost. That's easy to do, right? You look at every pair of 2 edges, flip them and see if they reduce cost, and keep doing it until you can't do it and you stop. It's a local optimum with respect to flipping 2 edges. Okay, but why stop at 2? Here is an example, right? Is this optimum? Does it look optimum to you? What would you do? What's a better tour? You should visit this guy like this, right? And you should replace it like this, right? Yeah? You can visually look at it, right? And say, this doesn't look optimum. So the right thing is what? Your green one is the right solution, right? Okay, but this will not be found out by just checking 2 edges at a time. If you want to flip 2 edges, I can't do this transformation. But if I allow you to flip 3 edges, I can do this, right? Okay, so you can try all possible ways of flipping 3 edges and figuring out whether it will improve the cost. Okay, that's called 3 exchange heuristic, right? So why is it called local? Because we're only looking at a small number of edges, right? There is no guarantee that we can optimize a big tour. It's just locally we are looking for improvements. Okay, and local search is very important for various reasons. I always like to tell this story about when I was working at, I used to work at Lucent Bell Labs for many years before I came to the university. So there we would design tools to develop low-cost networks and things like that, right, as part of my job, right. So one of the things, right, so what happens, right, a customer would come and say, I want something, and you design a network and say, oh, look, this is a cheap network, do you want it, right? So one of the things they'll do is the following, right, because these networks are not very big, maybe they have 30, 40 nodes, but they're expensive because they're optical networks, a lot of money, right? The networks are not too big, but the cost is high, right? So when you give a design to a customer, you know what people will do? They'll eyeball it and say, they'll do local search in their head, right? Or they'll plan, say, can I read, because they're paying a lot of money to you, right? So what will they try to do? Like, can I even save, like say, $100,000 because the equipment is so expensive? So they can try to tweak the design in a small way and see if it reduces the cost, right? But if they do it, then they will be upset with you, right? Because they say, I can, by looking at the design, can improve the cost by $100,000, and you're giving me a bad design because you're cheating me, they'll say, right? So even if you have a very sophisticated heuristic, if you don't do local search and check whether you can improve the cost, then you give it to a customer, the customer will do local search because it's their interest to do local search to improve the cost, right? And they won't trust your software, or they'll say you're not doing a good job of design because you didn't even do local search, okay? So even if you have a good heuristic, if you have to do local search at the end of the heuristic, because not all heuristics will come up with a reasonable local optimum, right? They may be very good heuristics, but they may miss a small local step, okay? So local search is a very important cleaning up phase for heuristics. That way you are guaranteed that there is no small minor improvement that somebody can notice and be unhappy about, right? This is in the context of customer service. But human beings are also good at local search, right? They'll look at it and say, can I improve it locally? So it's important both as a design principle as well as, there are many variations. Okay, there are many heuristics, of course, out there, right? SAT solvers, integer programming. Because integer programming is a very powerful meta problem, it makes sense to focus our energies on solving integer programming really well, or say solving SAT really well, and then using those algorithms via reductions rather than taking every problem that we have and trying to design a special purpose algorithm for it. So that's what happens, like the whole field of mathematical programming and operations research is really designed to develop important heuristics for special classes, but for specific problems like integer programming, linear programming, convex optimization, because they're generically applicable. Okay, and then you just use existing software for integer programming to model your problem, and then use some tweaks to make it better, right? But you don't design a custom, or if you try to design custom things, it's expensive or you have to spend a lot of time. Okay, so people spend a lot of time in integer programming, SAT solvers, and okay. Of course, there is a heuristics. Okay. So one thing, right? Why do we care about exact algorithms, right? The reason why exact algorithms are interesting, also both in theory and practice, is not just because they are nice, but it's a notion of robustness. Right? Suppose you take sorting, for example, right? What is the nice thing about sorting? We don't think about sorting anymore, right? Why? Well, first it is fast, but the fact is the sorting is done, right? In the sense that you don't have to worry about, will it give me the right answer? Will it give me an approximate answer? Will it work on this instance? Will it work on that other instance, right? The nice thing about exact algorithms is that you can forget about it once you solve it, right? While with heuristics, the problem is you can never rest, because maybe on this instance it will die, right? Right? Or it will give you a bad solution, right? So that's the lack of robustness is okay. So I'm going to now discuss this special class of heuristics called approximation algorithms. Okay. So what does the theory of NP completeness tell us, right? That the theory of NP completeness tells us that all these seemingly different problems are equivalent in terms of polynomial time exact solutions. Okay. That means that if you solve it exactly, this problem you can solve that exactly, right? All of these problems are equivalent. But somehow they don't behave as similarly when you actually work with them in practice. Okay, what does it mean, right? Is there any notion of that, right? Take the knapsack problem, right? The knapsack problem, if you ask practitioners, is the knapsack problem hard? They'll say no, it is not hard. Okay, it's very easy, they'll say. What does it mean? It's very easy. Oh, I can solve very big instances very fast. Okay, or I can solve very big instances to very good accuracy very fast. Okay, 1%, I will get you 1% optimality for knapsack in no time, don't worry, right? They don't think it's a bad problem at all. On the other hand, if you ask them to solve maximum independent set and maximum clique or Hamiltonian cycle, it's very easy to create hard instances. Okay. Okay, so empirically, even though all NP-complete problems allow you to reduce one to another, they don't behave in the same hard way in practice, right? So what explains that, right? So some are easier than others, right? One way to understand it, not the only way to understand it, is via the lens of approximation, okay? So what does approximation really mean, right? So let me first define some number of problems, right? Things we have seen, right? What is the knapsack problem? Everybody knows what the knapsack problem is, or not, right? I have n items, right? Each item has a size and a value or profit, okay? And I have a knapsack of some fixed size, okay? I can't take, I have to pick a subset of the items because I can't take all the items. The subset has to fit in the knapsack. What does that mean? The sum of their sizes has to be less than the capacity of the knapsack, okay? And I want to maximize the value of the items I pick. Okay, that's a knapsack problem. It's an NP-complete problem, right, when the numbers are big. We have seen vertex cover, we have seen set cover, Everybody remembers what set cover is? Yeah, it's a, right? And independent set, and the traveling salesman problem, right? The traveling salesman problem is given a graph, find me the Hamiltonian cycle with the smallest cost when there are weights on the edges. Okay, so they're all interesting problems. So here is what an informal definition of an approximation algorithm is, right? An approximation algorithm is a heuristic that always runs in polynomial time, right? It's not it's a polynomial time algorithm, okay? It always returns a feasible solution, okay? It gives out a solution. But it comes with a guarantee on the quality, the worst case quality of the solution it outputs compared to the optimal solution, okay? So two properties, it always runs in polynomial time, it doesn't do anything exponential, okay? It runs in polynomial time. It always returns a feasible solution, okay? The only issue is will it return a good feasible solution, right? What does it mean good? When we think of optimization, we want the optimal solution of, when you think of the optimal solution, we are thinking of a solution of smallest value or largest value, right? So the quality is the only thing it cannot give optimality for, right? So but it comes with a guarantee, it says, aha, I will give you a solution which is not more than this much than the optimum value, okay? So you can think of approximation algorithms are fast because they are efficient, they are polynomial time, fast estimation algorithms if you want, or bounding algorithms, right? Can you quickly get me a rough estimate of the optimum value? Okay, so that's what an approximation algorithm is. Okay, so here is what we know about some of these problems that are all NP complete. Okay, so what do we know about knapsack? If I give you a knapsack problem, I can give you a solution whose there's an algorithm which is very, very efficient, almost linear time, okay, n log n time, right, or in fact even better than n log n, right, which will give you a solution such that the value is at least 0.99 times the optimum value. It always returns a feasible solution, very efficient. It's guaranteed to give you a solution which is as good as 0.99 times the optimum value. It won't give you the optimal solution, because if it gives you the optimal solution, then it means it's P equal to NP, right? It's solving it. So it cannot guarantee optimality, right? But it will give you a solution which is as good as 0.99 times the optimum value. Every instance. Not for some and not for others. Every instance. So it's very good, no? I mean, I can make that 0.99 0.999. So if I give you a solution which is always within 99.99% of the optimal value, maybe in some applications you don't care, right? It's fine. Why, you don't care about this last 1%, right? The data is anyway noisy, who cares, right? So it's fine, right? So that's, in some sense, knapsack is very easy. Okay? So that's a good thing. Okay. Okay, for vertex cover, there is a very simple algorithm, we'll actually see it soon, that is guaranteed to give you always a vertex cover which is no more than 2 times the optimum solution vector. You may say that's not so good, right? You're giving me 100% worse in some ways than the optimum solution, right? Okay, but it's at least an estimation algorithm, right? It's an algorithm, you can say, given a graph, it will quickly tell you, is the vertex cover 100 or 1000, right? If you want to know, given a graph, quickly you want to know what is the smallest vertex cover size, right? It will tell you quickly, okay, it's not, it will give you an estimate within a factor of 2, which is not as good as the knapsack thing, obviously, right? But it at least gives you something, right? Okay, and moreover, you can prove that you cannot do better. What does it mean? It means that if there is an algorithm which will always give you better than a factor of 2 estimate, P equal to NP. Okay. So there is no algorithm which, if P is not equal to NP, if you assume that, or another way of saying it is the following: if you give me an approximation algorithm for vertex cover which is better than 2, that means it will give you always 1.5. I can use it to solve SAT. That seems like a bizarre thing, right? So even you can prove things like that, right? So anyway, the point is that once you use the notion of approximation, you can distinguish the difficulty of NP-complete problems. They don't look all exactly the same, right? So that is a good thing. What it allows you to do is like, some problems are a little easier than some other problems, and here is a quick estimation algorithm for you. Okay? It depends on the application whether this is useful for you or not. Okay? Suppose you are a big airline company which is trying to optimize how many planes should I buy, how many how do I schedule my airline routes and stuff. It's a very difficult NP-complete optimization problem, right? But if you're spending almost like $1 billion on purchasing airplanes, you would spend 10 million on a custom software to help you design the best you can, right? That's what operations research people do. They help you to solve smaller or a fixed size instance problem that an airline may have, because they really care about minimizing the cost, right? The cost is so high, it is worth spending millions of dollars and creating a custom solution for it. Okay? But if you are, say, you are serving ads on Google, right? You are doing, millions of optimization problems every second. Okay? Now, it's important, but it's not, each ad is not so important, okay? So you want a fast solution there, even though the underlying optimization problem might be a little bit hard if you want to solve it exactly, you are okay with a fast, nearly accurate solution, because you're solving like gazillions of ads problems every second, right? It depends on the application, the trade-off between speed, quality, cost, and development of the heuristic. Okay? So approximation algorithms are one simple class of problems which give you quick estimates, and I work in this area, and the nice thing about approximation algorithms is that they allow you to explore the structure of the problem just like we do for exact algorithms, like max flow min cut and other things. You can explore things. Okay, all right. So that is the background. Let's do examples of approximation rather than stay with formalities for too much longer. We'll come back to it, okay? Okay. Here is the vertex cover problem. Okay? Recall the vertex cover problem. Okay, come up with a nice heuristic for this problem. If I give you, I want a polynomial time algorithm that is a quick algorithm that will give you a feasible solution, right, always. Okay, and maybe it will do something okay. What would you do? You know that solving it exactly is NP-complete, so your boss came to you and said, can you come up with a quick and dirty heuristic for this problem? What would you do? Yeah. Yeah, right, you'd say, I want to, of course, picking all the vertices is a feasible solution. You wouldn't want to do that, right? So you'll pick the highest degree vertex, right, because I'll cover a lot of edges, right? And then you say, okay, I'll remove that, all the edges, then find the next in the remaining graph, find the next highest degree vertex, right? And remove it and remove it. Okay, that's a reasonable heuristic, right? Okay? What can we say about it, right? You can say, can we give any guarantee on how well it performs, right? Okay. This is a little bit hard because your mind has to change now. What does it mean that how can I prove that it does something interesting, right? It's a new class. Thinking about approximation is a little bit different in terms of how do we do the analysis. Okay, so we'll only scratch the surface in the next few lectures, but it's an introduction. Okay. Okay, everybody remembers what a vertex cover is, right? You already know, right? Okay. Okay, so here what you describe is a simple greedy algorithm, right? Okay, pick the vertex with the maximum degree, remove it, and keep doing it, adding, and output the cell set you picked. How well does it do? Okay, here is what we can prove. Okay, you can prove that for every graph, it will, actually this should be, the size of the solution that it outputs is no more than log m plus 1 times the optimum solution value. Okay, let's parse this for a little bit, right? Okay. So if the optimum is some number, it will output some bigger number, right? Because it is not an exact algorithm. It may output, does it run in a polynomial time, by the way? It's a simple algorithm, right? It easily runs in does it always output a feasible solution? Yeah, by construction it outputs a feasible solution, right? Because it takes, when it adds a vertex, all the edges, it covers all the edges incident to it and removes it. So it won't stop till all the edges are covered. So those two properties are simple, right? Okay, now the only question is how good is this algorithm in terms of what it does, right? So you can prove, and we'll prove it later in a more general context, that the value of the set it returns is no more than log of the number of edges plus 1 times opt. This is not a very good guarantee in some sense, right? So if the graph is becoming bigger, my guarantee is also getting worse, right? Yeah? If the graph is huge, I'm saying my guarantee is also getting a little worse, right? So it's okay that we can prove this, okay? We'll prove it later, right? Okay, but then you can ask, you have to ask, will it actually do that, or are you just not being able to prove something better? Okay? There are two questions. One is to say that it always guarantees this much bound, right? Then you have to ask yourself, is it because you have a proof that, I'll give you a proof later on that it does this. But then you have to ask, maybe it does better, maybe it will always give you a solution which is at most 10 times optimum, but you are not able to prove it, right? But no, we can prove the following also. There are many instances, an infinite family of instances, where this is really more or less the right answer, okay? That means there are instances where it will, as the graph is becoming bigger, the size of what it is outputting, the greedy algorithm, is also growing in this fashion. So more or less our analysis is tight. Okay. So now you have to ask yourself the question, why does is there a better approximation algorithm? Okay. Okay, this is a very simple greedy algorithm. Maybe it works well in many instances, but we can prove that in the worst case, it can behave badly, right? Maybe the worst case doesn't happen in your practice, but that's okay. But we can prove theoretically that it will do this badly. So I'm going to give you a different heuristic, which looks a little bit more magical, even though it's also extremely simple. Okay? Here is the other heuristic. Very simple. You find a maximal matching M in the graph G. What is a maximal matching? Not a maximum. Maximal. What is a maximal matching? You cannot add any more edges to the matching. But how will you find a maximal matching greedily? Maximal, not a maximum. What is everybody understand what a maximal matching is? A matching is a maximal if I can't add one more edge and increase the size of the matching. Yeah?
Just keep adding arbitrary edges until you can't do that anymore.
Yeah, let's start with any edge, okay, and try to add one more edge, right? If you can do it, right, and keep doing it, and then you'll get stuck at some point, because when you add an edge, remove the endpoints and all the edges incident to it, right? And then find another edge arbitrarily, right? So this is a linear time algorithm, right? If you maintain the data structure easily, right? Okay, then it's arbitrary maximal matching. It may be very far from optimum matching, right? And so I find that very simple, very easy algorithm, right? And then my solution is take all the endpoints of these edges. Both endpoints, not one, both endpoints. Okay? Simple algorithm, yeah? Polynomial time algorithm, right? Okay, now, is it a vertex cover? So what did I do? So let's draw a graph. Give me a maximal matching in this. Let's see, okay? Maybe I pick this edge, and then what should I do? Maybe I pick this edge, and this edge, and can I do one more? I'm done, right? Yeah? Okay? Okay, so what am I outputting? I'm outputting this, right? I find that first, and then I output this, 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 this. Okay? Yeah? So, is this a vertex cover? Okay, okay, true. Why is it always going to be a vertex cover? I want to argue that this algorithm will output a set which is a vertex cover. Suppose not. What does it mean that it's not a vertex cover? If a set is not a vertex cover, what does it mean? There is some edge which is not covered, right? Oh, but I should have added it to my matching, right? My matching would not have been maximal then, right? If there is a Mason edge which is not covered by set S, I could have added that edge to my matching and still it would have remain a matching, right? Yeah? So you agree that it's a feasible solution. Now the question is can you prove something about how good is this? Right? Okay. My claim is the size of, first we proved this, right? S is a feasible vertex cover. I claim that, optimal solution value must be at least the number of edges in my matching. Why? So I claim in this graph the optimum solution value is at least 3, not 6, right? We are outputting a set of what size? 6, right? Because we took 3 edges and both endpoints of those 3 edges, right? Okay, that was important because that's the only way we could prove that it's a feasible vertex cover, right? Yeah? Okay, but I claim in this graph the optimum vertex cover is at least of size 3. Why is that? Because I had 3 edges in the matching, I claim it's at least 3. Why is that? What does it mean that this is a matching, right? Take any matching in the graph. Okay? How does the matching look like? It looks like this, right? Okay. What does it mean it's a matching? It means that their endpoints don't intersect, right? How will any vertex cover this matching? Every vertex cover must have at least one endpoint from each edge of the matching, right? Yeah? So every vertex cover must have size at least the size of the matching. Okay, in fact, every vertex cover must have a size at least the maximum matching, right? But this is not even a maximum matching, it's a maximal matching. So definitely it should have at least the size of the maximal matching. Yeah? How many did we output? We output 2 times the size of the matching, and it's a feasible solution. While, so our algorithm is always guaranteed to output no more than twice the optimum value. Yeah? Make sense? Yes or no? Huh? So it's a better algorithm than the greedy algorithm, no? In what sense is it better than the greedy algorithm? It is guaranteed to give no worse than 2 times for every graph, and it's very simple, very fast, right? No slower than essentially the greedy algorithm. Okay? While the greedy algorithm has the property, in some graphs it can give a very bad solution. Okay, there are graphs where, very big graphs, right, where this bound can be made arbitrarily large, right? If I take a graph of size 10,000, this can become 100. So there the greedy algorithm will give a solution which is 100 times optimum value. While this algorithm is guaranteed to give only twice the optimum solution. Okay, so it's not obvious, no? So that's why approximation algorithms are interesting. You cannot simply figure out how to come up with approximation algorithms, even though you can come up with heuristics easily. Okay, so you need to analyze, how well does this do? Okay, okay, okay. So that's the two approximation. Now, what would you do? Now we should do some local search on this, right? This algorithm, is there any? Can we remove any of these vertices and still remain optimal? Which one would you remove? Remain feasible. Can I remove this? Right? Okay, I can remove it. Right? I should remove it. Okay. If I go to a customer with this, they'll complain. Right? Okay. So even though this approximation algorithm is guaranteed to give you a two approximation, it may not give you a solution which is minimal even. Okay. So you can make it minimal, right? But that's something that one has to do, right? And maybe you can even improve it a little bit. I am not sure how to do it right now, but that's an important aspect of heuristics. Can give you solutions which are not even minimal. So you need to do some post-processing. Okay. All right. Okay. Now I want to do one more very powerful and perhaps the more powerful general technique is via using linear programming or some kind of mathematical programming relaxation. Okay. To illustrate that, let's go and say, how would we reduce vertex cover? Now I'm going to consider even a more general problem. There are weights on the vertices. Okay. That is, each vertex has a weight and I want a vertex cover with minimum total weight. Right? It's a more general problem and the matching heuristic doesn't work actually. The greedy algorithm kind of works. What would you do for the greedy algorithm? What is the natural modification of the greedy algorithm if vertices have weights? That is, every vertex has a weight now. Some vertices are very expensive, some are not so expensive. So if you just look at the degree, it may be that it has good degree, but it's a very expensive vertex. I don't want to pick it. Right? How will you modify the greedy algorithm when the vertices have weights now? You can do the weight divided by degree, right? That's the bang for buck, right? If I pick this, I'll cover this many edges, right? You try to minimize that, right? So you can do weight divided by degree and you can prove that the analysis still goes through, okay? But the matching algorithm doesn't have a nice weighted version if you don't think about it very carefully, right? Okay. Okay. How would we reduce vertex cover to integer programming, right? We already saw that. We said, can we reduce vertex cover to integer programming? Well, what are we choosing, right? We want to decide for each vertex, should we choose this vertex or not choose this vertex, right? So the variables are, what are the variables? For each vertex, there is a variable xv, and we want to take it as 0 or 1. 0 means we don't want that vertex, 1 means we want that vertex. Okay, what are our constraints? We want to make sure that for every edge uv, at least one of the endpoints is taken, right? So xu plus xv is greater than or equal to 1, right? And then we want to minimize the weight of the vertices we pick, right? So we want to minimize some v belongs to capital V, wv, xv, right? Okay, this is an integer program. Obviously, if we can solve this integer program, we'll solve vertex cover, right? But it's too hard, so integer program is hard, and so vertex cover is not easy to solve. So what can we do? We can say, okay, look, I can't solve the integer program, but I can solve the linear program by relaxing this to between 0 and 1. I'll let you take fractions. Okay? Agree? Okay. So suppose I solve this. Given a graph, I solve this, right? Okay. What do I get? Given a graph, I solve this linear program. What do I get? I get some number, right? What can I say about that number? Will the number be bigger than the optimum value or smaller than the optimum value or equal to the optimum value? It should be smaller, right? Why? Because I'm taking the integer constraints and dropping them and saying, oh, just make them even fractions, right? Right? So what I get by solving this is a lower bound on the optimum value. Yeah? See, remember when we are doing branch and bound, we wanted a lower bound, no? you can solve the linear program and you get a value and say, ah, okay, the optimum cannot be less than this. I know it for sure, right? That's the nice thing about solving linear programs, right? It's called a linear programming relaxation of the integer program, right? This is what the vertex cover integer program is. This is called the linear programming relaxation, right? Okay, now I get some number. Can I use the number, and not only do I get a number, right? I get some fractional values, right? This vertex is taken to what? 0.2. That vertex is taken to 0.3. That vertex is taken to 1. This vertex is 0. I get some fractions in addition to the solution, right? Can I use that information to come up with an algorithm and give you a feasible solution of cost not too bad compared to the fractional value? Okay, that's called a rounding. Why is it called rounding? Because if all the vertices are integer valued, I'm done, right? I know I get, suppose I solve this and magically the vertices all have zeros and ones. Hey, great, I'm done because I solved the LP, I got zeros and ones, and that's what I wanted, right? But it won't happen always, right? Okay, but can we use the information to do some rounding? And yes, you can, right? Okay, so we solve this LP and say X star is an optimum solution to this linear program. As we discussed, the optimum value is at least the value of the fractional solution, right? Okay, okay. Here is what's called rounding. Let's do the rounding follows, right? We look at all the vertices and we pick in our set any vertex whose fractional value is at least half. Okay. Okay, remember, okay, so here is a graph, right? Okay, can you tell me what optimum value for this would be? All weights are 1. If I allow you to use, what is the optimum value here, by the way? How many vertices do I need to take? Will 1 do? If I take only one vertex, then this edge won't be covered, no? So I need to take 2, no? Yeah? Opt is what? What about if I allow you fractions? Can the value go down? What is a feasible fractional solution? That means I allow you to take each vertex, but the constraint is that for every edge, you have to make sure that the sum should be at least 1, right? Yeah? What if I put, is that feasible? Yeah? But what is the value of it? So let me call this opt LP to distinguish it from the fact that it is not integer optimum, is what? 1.5, right? It's less, right? Obviously it will be less because it's going down. It can choose fractions. Okay, what is my solution? What I'm doing is I'm taking every vertex which is at least half. Okay, so what does it mean? In this solution I'll take all 3 vertices, right? So what do I get? I get 3 instead of 2, right? Okay, okay. Well, okay, that's my algorithm. What do? Given the graph, I will solve this linear program, okay, and I get fractions on the vertices, and from the fractions on the vertices, I'll create a set of vertices which is all the vertices which have fractions which are at least half. Okay. First, I want to claim that the set I get is actually a vertex cover in the graph. Why is that? Can there be an edge such that both endpoints are not in my set S? Why is that? Because the sum of those fractions should be at least 1 if it is feasible solution, right? For that edge, we have a constraint which forces us to have that x star u plus x star v is greater than or equal to 1. It means that at least one of them has to be half, right? Or bigger, right? So we would pick maybe both, right? Or we may pick at least one. So we will get a feasible solution. Okay, what is the weight of the set I pick? I want to claim that the weight of the set is no more than twice the value of the LP solution. Yeah? Why is that? Okay, first you agree that S is a feasible vertex cover, we agreed that. And then I want to argue that the weight of the set is at most 2 times the weight of the fractional solution. And because the weight of the fractional solution is no more than the weight of the optimum solution, I can prove that it's at most 2 times the opt. Right? Why is it at most 2 times the weight of the fractional solution? When did I pick a vertex? Only if in the fractional solution it was at least half, right? But the LP in the fractional solution paid at least half the weight of the vertex. Right? Remember, the objective value is what? Sum of WV x star V, right? So I'm only picking vertices which have x star V at least half. So maybe LP paid half, I am paying 1, right? So vertex by vertex, the weight of what I am paying in S is no more than twice the way what the fractional solution paid. So the total weight of the set S is at most 2 times the total weight of the fractional solution. And the weight of the fractional solution is a lower bound on the optimum integral solution, right? So I get a 2 approximation this way, right? What is the difficulty with this algorithm? The only difficulty is that you have to solve the linear programming relaxation, right? So of course we know LP solving is in polynomial time, but LP solving is a more difficult task than the simple greedy algorithm I gave you earlier, right? Okay. But LP solvers are pretty good. They have many more interesting properties. So as long as your LP is not too big and not too complicated, the LPs tend to give you good solutions. That's separately true. Okay. Okay. So the nice thing about LP is also it gives you a lower bound automatically, right? A computable lower bound which will help you figure out certain other things as well. Okay. And then you can try to solve the integer programming by using LPs repeatedly and doing branch and bound and stuff. That's a big area that we won't go to. Okay. So we saw different ways of designing approximation algorithms for vertex cover, right? So let me say something about vertex cover and set cover. We saw that vertex cover is a special case of set cover, right? The greedy algorithm generalizes to set cover very naturally. You pick the largest set, remove all the elements covered by that set, which is what exactly this greedy algorithm for vertex cover is doing. Okay? One can prove that the greedy algorithm gives you this approximation, and that's the reason why it also gives the same approximation for vertex cover. Okay? The important and interesting and highly non-trivial result is that unless P equal to NP, for set cover you cannot do better than that approximation. Okay? The simple greedy algorithm is optimal unless P equal to NP. Optimal in the sense of giving a worst case guarantee. Okay? And also for vertex cover, you can prove unless P equal to NP, there is no 1.36 approximation. You cannot do better than 1.36. And in fact, people believe under, again, something which I won't go into, that you cannot do better than 2. People have tried, right? Why is 2 good? Maybe there is a better approximation, right? Why did you stop at 2? Why are you so satisfied, right? Maybe there's a 1.1 approximation algorithm, which will be much better than a 2 approximation, right? But one can prove that you can't do it. Well, maybe, P equal to NP, in which case everything is polytime solvable. But you prove that unless P equal to NP, you cannot do it, right? Okay, that's one thing you can do. Okay. Now I want to talk a little bit about why approximation is subtle. Take independent set problem. What is the independent set problem? I give you a graph and I want to find largest independent set, right? Yeah? We saw a reduction from independent set to vertex cover, remember? Okay, how did you do the reduction? If G is a graph, S is an independent set if and only if the V minus S is a vertex cover. You can say, okay, good. Here is a heuristic for independent set. Given a graph, compute a vertex cover and take V minus X as an independent set, right? We already saw nice algorithms for minimizing vertex cover, right? So you find a small vertex cover and take all the other vertices. They must be an independent set, right? Is this a good algorithm? Okay, what does it mean it's a good algorithm? Well, if I had an exact algorithm for vertex cover, this would be an exact algorithm for independent set, right? But okay, but I don't have an exact algorithm, but I only have an approximate algorithm for vertex cover, right? So what happens, right? Okay, here is a reason to say that no, it is not a good approximation algorithm. Okay, why is it? Let's understand it. Suppose K is the minimum vertex cover size, okay, and let's suppose it is n over 2. Okay, if it is very large, then where n is the number of vertices, I have a 2 approximation, say. What is the 2 approximation in this case? I can give you the entire vertex set, no? Even if I give you the entire vertex set, I will get a 2 approximation because K is n over 2, right? In this case, what will the algorithm do? It will give nothing. V minus S is what? V minus V, which is empty set. Okay. Okay. Or think of it this way. Suppose K is n over 3n over 4. Okay. What does it mean? The minimum vertex cover is of size what? 3n over 4. Then what is the size of the optimum independent set? Alpha of G, which is the independent set size, is what? N over 4, right? Okay. If I give you a 2 approximation for vertex cover, what does it mean? It's going to give me a vertex cover of size at most what? 2 times 3n over 4. So that is what? That is more than n, right? So it can give me anything it wants, right? It can give me the entire vertex set and it will still be better than 2 approximation, right? But if you take the complement of that, I get nothing in the independent set. Okay? So that heuristic can give me the empty set for independent set, which is obviously not a good approximation because there is a huge independent set in the graph, no? N over 4, and I'm giving you nothing. Okay? So what this means is that vertex cover, just because vertex cover reduces to independent set in the exact sense, doesn't mean that in the approximate sense a heuristic for vertex cover will actually give you anything interesting for independent set. Okay? In fact, the following is true. Unless P equal to NP, there is no good algorithm approximation for independent set in the worst case. Independent set is a really hard problem in the worst case, not in some practical scenarios. In the worst case, independent set is a really hard problem to approximate. This is how bad? You can't even really get a close to n approximation. It's really terrible in the theoretical sense. On the other hand, it's very easy to transform vertex cover into independent set, and it's very easy to get a good approximation for vertex cover. Okay, what this shows is that even though vertex cover and independent set are very closely related in the exact sense, they're very different when you want to approximate them. One is much easier than the other. Okay, vertex cover is much easier to approximate than independent set. Okay, so that is something to keep in mind, that problems that are equivalent in the exact sense are not always behave the same way when you are allowed to approximate. Okay, all right. Okay, so that's it. We will discuss a few more approximation algorithms next week to give you a flavor of simple problems, simple ideas, and more or less I will conclude the class. Okay? Okay. Have some good turkey, and if you're a vegetarian, I guess you ought to figure out something else and come back relaxed.